Hello and welcome to the third lecture in the video lecture series of the course Operating System. In this lecture 2, we'll be continuing our discussion on the fundamental concepts in OS. We'll initially begin with a more detailed understanding of the processes, then we'll move on to discussion about discussion on interrupts, and finally we'll discuss about implementation of system calls. So let's begin our understanding of process. So in the last class we discussed about a term called process, which is nothing but a program in execution. That is, whenever a program is about to be executed by the CPU, we term it as a process. Program is only some piece of code and data, but the moment it starts executing, we call it a process. So say we have a program called f1.c. This f1.c is compiled, and compilation of that results in an executable, that is the instructions given in the program in the form of some high level language instructions are now converted into the instructions understood by the machine, and that is called the machine level instructions. So the executable is nothing but these machine level instructions, and now once the machine level instructions are available, we want this to be executed. So in order to execute or run that, we type in at this prompt, that is at the terminal, we type in the /a.out, and that instructs the CPU to execute that. Okay. So this is how you run a program, right? So whenever a process is created, the first thing that the OS does is it allocates a physical memory to the process. So say for example, a process called a.out has been created here. So the moment this a.out process gets created, OS allocates certain range of address locations to this. So this is this a.out process, and the range of address locations which this process the OS gives to this process is called its address space. So every process, the moment they get created, an address space is allocated to it. Now this address space that I have written here, I have intentionally given this to be a range of contiguous locations, but they may not be. Okay. So this a.out process that you see here may be sitting in this physical memory. Okay, so this is the physical memory, the memory with which the CPU interacts. So this a.out may be sitting in a distributed view. Some part of this a.out may be here, some part may be here. So both of them are some portions of this process called a.out. So that can be a possibility. It may be contiguous, it may be distributed. So distributed kind of storage of the process allows other processes to be allocated within the physical memory. Okay. Now, in addition to this actual storage of this, the compiler also does something. And what the compiler does is, the compiler also allocates a range of address to this particular process. Okay. And the compiler, the range of address that this compiler allocates is called the virtual address. So this is also a memory image of the process called a.out. So now you see you have two views of this particular process. One, the actual view, that is the actual locations allocated to that particular process by the operating system, and the other which is done by the compiler. Okay. And this is a virtual address range. And as you can see, the range that this compiler has allocated to this particular process, it depends on the architecture. That is the register set that is available to that particular machine. So often the size of the machine is governed by the size of the register that is present. So suppose it's a 32-bit machine that the registers are of size 32. So the maximum addresses that can be generated out of this, for this 32-bit machine is 2 to the power 32, because the address which is being generated or by the CPU is through a register called program count. So if that is of size 32, so the maximum range of addresses that can be generated is from 0 to 2 to the power 32 minus 1. So that means these are the range of addresses that at max that can be generated, and that is nothing but something of the order of 4 GB. So for a machine which has 32-bit registers, the range of addresses that can be generated is approximately or is 4 GB. So at max, a compiler can allocate a 4 GB address range for a process. So the memory image of a process that a compiler allocates depends on the architecture. So let's say the compiler in this case has allocated certain range, may not be 4 GB, so that's the maximum range I'm talking about. So let's say it's given some 0 to some m minus 1. So m number of locations it has allocated for this A.out. Okay. So however, this is the actual space that is occupied in the physical memory. Now they are completely different. Okay. But interestingly, the one that is allocated by the compiler is the view that is seen by the CPU. So what the CPU looks at is not its actual view, but the one that is generated by the compiler. That is its virtual address range or the virtual memory image. Okay. So obviously the CPU, when it generates or instructs or wants to execute certain instructions, it assumes that the instructions is available in this memory range, and accordingly it sends the instructions, so sends the addresses. So when the CPU sends an address in order to fetch some instruction, this address is not the actual address which is available for the process sitting in the physical memory, but the address is the virtual address, or we call it the logical address. Okay. So what the CPU sees is a range of contiguous locations that have been allocated to this particular process called A.out, and I want any one of those locations from that contiguous memory locations. However, this particular, the instruction that the CPU is looking for is available from the physical memory. So the OS now takes charge, and the OS, it knows the mapping of each one of those address locations in the virtual address, virtual memory map, to its actual position in the physical memory. So this is the role of the OS, that is, it takes this address and it finds the corresponding mapping, that is the actual location of that instruction in the physical memory, and then provides that particular instruction to the CPU. Okay, once we understand that how the process is allocated two different views of the memory, now there can be situations where the process may like to execute instructions which that process is not supposed to execute. Say for example, the process wants to execute or access some hardware. We have already seen that such kind of hardware access the process cannot perform. So it is the operating system or the kernel that performs these operations on behalf of the process. And how does it happen? The OS requests, the process requests the kernel by using some system calls, and the kernel executes those system calls, that is that particular set of instructions, and then returns the result back to the application. So let us say there's a situation where that such kind of an instruction has to be executed by the CPU. Okay, but since that instruction is to be executed by the OS, obviously those instructions will not be available in this range of addresses allocated to the process in the physical memory. So what happens is the operating system, the portion of the operating system, the kernel code of the OS is actually mapped to the address range, the virtual address range of this process. So as you find here, the OS code is mapped to the virtual address range, which means that some portion of, if this is the virtual address range of the process, some portion of this particular virtual address space, maybe let's say some portion of this process called a.out. A portion of this is actually pointing to not the address locations of this range of address. If they are accessed, the OS understands that this range of address locations that has to be accessed will not be available in the address range allocated for the process in the physical memory. Where will they be available? They will be available from this portion, the one that I have. Okay. So the memory management unit that actually takes care of this mapping will understand that these range of addresses of this process called a.out, which are requested currently, will not be available in this process, in this actual locations of this a.out. They will be available within my code itself, and accordingly those instructions will be fetched from the kernel and will be provided to the CPU. And remember that when the CPU would be executing these instructions, the CPU itself will be switching to the privileged mode. So this is what is and how the virtual address range and the physical address range of a process is maintained. So let's summarize. Whenever a process gets created, there's a certain range of address locations that are allocated to that particular process. We call it the address space. Now the address space of a process which actually resides in the physical memory can be contiguous or it can be distributed. That is, some part of it will be in some portion of the physical memory, some part of it will be elsewhere. Now apart from this, the actual physical location of this process, there is one more view that is created of a process, and this is done by the compiler. So when the compiler compiles the code and a process is ready, it allocates a certain range of contiguous address locations to that particular process. Okay, say for example in this a.out. And the range of addresses that can be allocated to a particular process depends on the architecture. So if it is a 32-bit machine, the amount of addresses that can be allocated is at max is 4 GB. Then the next thing that we discussed is this virtual address range, the virtual address space that is allocated to this particular process. Some part of that actually points to the OS code. Okay, and why is that? Because many times during the execution of a program, there will be a situation where the process will be requesting for some I/O access, and that I/O access has to be done by the OS. So if it has to be done by the OS, that is nothing but some OS code that needs to be executed. But the OS code is not part of the address range allocated to this a.out. That is here. So that means some part of the virtual address range should have, some part of this virtual address range should have a pointer to the OS code. Okay. So later on, when we discuss more about the process in the next lecture, you will come to know how the operating system actually maintains this mapping between the virtual address space and the physical address space. Okay, let's talk about the dual mode of operation of a process. We already have seen this, but let me recap. So what we found is that if a process has to be executed, the process has to be loaded onto the memory, and then the CPU has to instruct the process to execute. Now there can be situations where you can have multiple processes that would like to be executed on the CPU. Okay, so think about a situation where you have more than one process. So this is a process called P1, then we have a process called P2, then we have a process called P3, and each one of them has a virtual address map, P1, P2, P3. So this is the virtual map of P1, this is the virtual map of P2, this is the virtual map of P3, and the CPU would be executing each one of them. Okay. Now, in this situation, it is very essential that you keep some kind of isolation among the address ranges allocated to P1, P2, and P3. So it's not only among the processes, it's also important that you maintain an isolation between the address range of a process and the address range allocated to the OS code. Okay. So in order to do this, in order to ensure isolation, we already have seen that the processes, they have a dual mode of operation. That is, a process either operates in the privileged mode or it operates in the non-privileged mode. So there are two modes of operation of a process. Either it is privileged or it is non-privileged. So during the privileged, non-privileged mode, the process runs its own code. Okay. And in the privileged mode, it's actually not the process but the OS that runs these instructions. So it's the OS code that gets executed. So as you see, during execution of a process, there can be situations where the process would like the help of the OS to get it done. Say for example, for an hardware access, the process needs the help of the kernel or the OS to get that job done. So during this time, it's actually the OS code that is executing. So it's something like this, that the process P1 is executing till this portion and suddenly it hits upon an instruction and then it wants this OS code to be executed and then again it will resume the rest. Okay. But if you allow the process to execute the OS code, then it may so happen that it can tamper the OS code. So it is better that you allow the OS to execute this code and not the process P1. So when this process P1 was executing, okay, we say that it is a non-privileged mode. And during the time when the particular process P1 wants some privileged instructions to be executed, it transfers the control to the kernel. So it transfers the control to the kernel and the kernel executes that. Okay. So that means, so this is the privileged mode that is executed by the kernel, and once the kernel is done, it again returns the control back to the process. So the process again resumes instructions from here. Okay. And this can happen multiple times in the process. So what we understand is that every process will require some time or the other, some OS code to be executed. So it's important that some portion of the OS code is mapped to the virtual address range of the process, which means that the virtual memory map of the process P1, which is maintained, must have some pointers to this particular code. Okay. And that's already what we have seen when we were discussing about the virtual address map. Right. So when the CPU would like to access these instructions, which are nothing, which these instructions of the process P1, since they are mapped to the some locations in the OS part of the address range, immediately the process P1, it actually transfers the control to the OS. The OS executes them, and then once the kernel or the OS has completed the execution, it returns the control back to the process P1. So this is a dual mode of operation, and the hardware also participates in that by changing it from the by changing its mode, and the moment the OS code runs, the CPU becomes privileged and it executes it in the privileged mode. So this is how the dual mode of operation of an OS takes place. Okay, now let's proceed towards another very interesting concept, and that is the interrupts. We already have discussed something about that in the last lecture, so let's quickly go through it. So interrupts are, as the name implies, it interrupts the running process. It breaks the running process. Oh, okay. Let's say interrupts are running process. What do you mean by that? We mean that suddenly there were some instructions that were currently being executed, okay? And suddenly something happens, and instead of executing the next instruction, let's say instruction I1, I2, I3, I4, and I5 have been executed so far, and now something happens, and instead of executing I6, you jump to some other instruction, let's say I50, and you go on doing that. And once you are done, you may come back to execution of I6 again. So this is what we call an interruption to the normal execution of a program. The program was executing one by one, and suddenly you create an interruption and you jump to a different set of instructions and you start executing that. Okay. Now, when I say that, okay, something happens, what are the things that can lead to this kind of instruction or this kind of interrupts? Okay. So there are three possibilities which can happen, which may be the cause of an interrupt. One is you can have, some physical event. Let's say the CPU, which was executing this, has some line through which some device, so this is the CPU, and this is some input-output device, through a certain interrupt line, it informs the CPU that please stop your execution and jump to this particular location and start executing the instructions written there. Say for example, when you type something on the keyboard, that's a kind of an interrupt. Okay. The CPU is actually executing some instructions in the background. Suddenly you type something on the keyboard, and through the keyboard controller there is a line that gets connected to the CPU, and it informs the CPU that you should stop your current execution and jump to the instructions that I would like you to do. Okay, so this is a typical the typical way in which an interrupt can be generated. It's a physically generated interrupt. Okay, now when I say that I jump to this particular location, the location that I jump to is again there's some program which is written there, and I start executing. So that interrupt forces the CPU to start executing instructions written from a certain specific location. And the instructions that are executed on event of an interrupt is called an interrupt handler, or we also call it an subroutine, an interrupt subroutine. Okay. So what happens here is that for different interrupts, there are different locations which are already predetermined. Okay. So that means if you have, let's say a CPU has a certain interrupt line, let's say interrupt line 1, interrupt line 2, and interrupt line 3. So for each one of them, there's already predetermined that if there's some interrupt that comes through this particular line, the CPU will be taken to this location. If it comes to this line, the CPU will be taken to this location. So the interrupt handlers for each of those interrupt lines are well defined. So they will be available at that particular location. And interrupt vector is, so what interrupt vector is, it contains addresses of all interrupt handlers. So you can think that in terms of vector, which contains, this is the address that points to interrupt handler 1, this is the one that points to interrupt handler 2, and so on. So this is the interrupt vector. So this is how the interrupts are serviced. So the moment an interrupt arrives, the CPU, it looks up into the interrupt handler and finds out which interrupt has arrived, and accordingly it jumps to that address which is maintained here. So this is, say, interrupt number 1, interrupt number 2, and so on. So accordingly it decides which interrupt has come and then jumps. So this is how interrupts occur through physical events. Now there can be other ways of interruption of a program as well. The second way that may lead to an interruption of a program is the occurrence of errors or exceptions. Now it may so happen that during execution of a program, you end up into some kind of an execution that you don't. Say for example, some computation by zero or buffer overflow. So these are the situations which can happen. So in that case, that you would like the execution to stop and jump to some other location where you have written what to do if this particular situation arrives. So such kind of interrupts we often refer to as trap. Okay. And the third is the software generated interrupts, where you are forced to jump to some other range of locations. The CPU starts executing some when a certain instruction arrives. Pretty similar to what we have been discussing so far. System calls are a kind of software generated interrupt. So during your execution of a program, suddenly you come across some instruction called printf, which eventually is nothing but a write system call. So when the CPU comes across this kind of instruction, it understands that, oh, this is not the process to be executed, this is not an instruction that this process has, or this is not the instruction of the process, so I have to jump to some other location, where the locations of the kernel, right? So that's again an interruption to the normal execution of a process. But this time, it is generated not asynchronously through some event, or neither it is generated due to occurrence of an error. It's through a predefined instruction that I know that if this instruction arrives, this is what has to be done. So this kind of interrupt generation is called a software generated interrupt. Okay, and an operating system, you can say, an OS, it is an interrupt driven software, because whatever we saw in the discussion which we have done so far, we came to know that the primary goal of an operating system is to allow user applications to run smoothly, and it provides an interface to do that, and that interface is nothing but system calls. So majority of the times you will find that applications, when they execute, they end up into some request to be made to the OS. That is some kind of a system call that has to be executed. And a system call is nothing but a software generated interrupt. That means you keep on switching your execution from process to an OS code and back to the process code. So this goes on. So that is the reason why we say that OS is interrupt driven, because the system calls are the software generated interrupts, and the interface between the apps and the OS. So that is the reason why we call it an interrupt-driven software. Okay, so now that we have some idea of how an OS works and what exactly is the role played by OS, let's summarize what the OS does. Okay, so if we summarize what an OS does, we primarily find that the OS is mainly related to handling processes. We already have seen that it's nothing but some kind of mechanism by which the programs interact with the hardware. And we don't say program now, we say processes. So we have processes, and the OS, what it does is it primarily handles them. Okay? That is process management, you can say. And what does the OS do? The OS provides different ways to create a process, to modify a process, to delete a process, that is to destroy a process. So these kind of different mechanisms, it will come across all that. How the OS helps in working with processes. Then we saw that how it can manage the processes. Okay, so for that it needs some kind of process scheduling to decide which process will be given a chance to access a certain resource. Then when multiple processes work on a system, it's obvious that these processes would like to interact among themselves. So we would like the processes to be interacting among themselves, and that's what we call the inter-process communication. So we'll see how the OS handles inter-process communication. So that's one of the major things that an OS does. And it also, when processes communicate, it's very essential that they maintain synchronization between the operation of the two processes, or else there will be a mismatch in the data transfer. So that means the inter-process communication should be associated with some kind of synchronization mechanism. So the operating system, one major job of an operating system is to maintain synchronization among processes. And then it performs some kind of memory management. We just saw the requirement that a virtual address map has to be translated into its corresponding physical addressing. So that is what is done by the memory management unit of the OS. And then we have finally the I/O and file management. So that is again a very important thing that the OS does, that it finds out how a block of code, which we usually call a file, actually can be it will be having an equivalent form of a process. So the one that is maintained as a block of array, that is an array of some bytes stored in some portion of some storage device, what is its corresponding form when it gets loaded in the memory? So the relation between the two and how the data that is to be stored in that particular device, how will it be done in an ordered way so that you can retrieve the data from there. So that is what is the job of an OS regarding file management. So you see, this is the primary job of an operating system. So when it comes to deciding how to design an OS, then the things that one needs to keep in mind, that is, if I decide to design an OS, there are some modules that I would like to keep or I have to design. Primary among them will be first some kind of an interface. Okay, what interface? The syscall interface. so that applications which sit on top of that can utilize this system called interface and can make or perform any one of those modules that I will be describing next. So the first thing that we should have in any operating system, that is, I'm specifically referring to the kernel, is an interface, which is called the system call interface. And followed by, we'll have modules that will be used for process management. So modules that will help in creation, work, deletion, modifying processes, process scheduling, etc. So all this will include the process management module of the kernel. Then we'll have a module that will be related to memory management, okay, that is responsible for the virtual addressing to physical addressing, the translation. And then we have something related to the file management. Okay. We have, and then we have, so this is the utilities that we expect to be present in the kernel. This is the mechanism through which these utilities will be accessed by the application programs. And this, all these management techniques, the three management that we are talking about, what are they used for? They are used for access of hardware. So sitting at the bottom is the hardware. But now every hardware has its own code, right? So the access mechanism of every hardware is different. So the code related to a certain specific hardware, the code in order to make that hardware work is what we call its device driver. So what you have in the kernel is a group of this code called the device driver. So if you look at the modules that should be present in any OS, these are the ones that are at least necessary to develop a kernel. So you must have modules to manage the process, modules to manage the memory, some module to control and coordinate and work with the different files, the file system. And then there must be the code that actually will be used to access a certain hardware, which we call the device drivers. So this is what forms the kernel. Okay. Now, if all these modules are part of a single code, that is one single code that contains the entire, all these modules, such kind of an OS that you develop is called a monolithic OS. One big code that contains all the modules. Okay. So there are advantages and disadvantages of having this kind of design. The advantage is that that's a standard way of designing. You keep everything at one place, and for every request or for any module that of a kernel that a certain application would require, will be requesting, and the kernel will look up and then will execute that particular module. That's how it will work. The disadvantage is that gradually, as you put more and more functionality into these modules, this, because it's one single code, the kernel becomes bulkier. Okay, and that's often not feasible to be run on certain hardware. So there's a hardware limitation that comes up the moment this kernel becomes bulkier. An alternative to that could be that you strip out some important functionalities of the kernel, some not so important functionalities from the kernel, and run them as user application processes. They are something. These programs will be kernel level routines, but they would be run in the user level process. because they are not so important. Let's say something of this type, maybe the important parts such as, say, the IPC, the synchronization, okay, and interrupt schedule, etc. So that can be part of the kernel. Let's say the IPC, the synchronization, the scheduling. So you keep this in the kernel, and for the rest of them, let's say the file system services, that you may not put in the kernel. You can run this as a user level code. Okay. So it's like this, that if an application would like to access the file system, okay, so the file system, since it's not present in the kernel, okay, has to be run in the user space. But it's not direct. It's not direct that the application will be able to run this file system. It has to go to the kernel. So the application will put its request to the kernel. The kernel, in turn, will forward it to this file system service. So think this in this way, that all the non-essential services that were originally part of the kernel now have been taken out and have been created in the form of utilities or services. So there can be many such services, each one of them. And these services are actually kernel code but running in the user level, in the user address space. So whenever those services have to be invoked or required, the code, that is the application code, the program that would like to execute them, would put the request to the kernel, and the kernel's job is only to test whether that particular request is a bona fide request, it's a proper request, and if it is, it simply forwards it to the corresponding service. The service then looks at the request, executes and sends it back to the kernel. Kernel then forwards it to the application. So this kind of design of an OS is called a microkernel, where the kernel is a lighter one. It contains only some very essential, functionalities. The rest of them, it acts like, forwarding it to a third-party service, which is running in the user space. However, the service that is being run is actually a kernel service. Okay, so that's the job of the kernel to do, but the kernel is actually running that as a user program. So that's how it works. So there are some operating systems that prefer monolithic code. Linux is an operating system that prefers a monolithic way of design. However, there are other real-time operating systems that prefer the microkernel approach. So these are the two basic ways in which the two ways of designing an OS. Okay, so now let's complete this lecture by having a look at the system calls and how the system calls are implemented. Okay, so we have seen so far that system calls are nothing but some kind of an interface, okay, or between the application programs and the kernel. So the system calls, they are an interface between the apps and the kernel. And this is the way in which applications, they request some job to be done to the OS. So this is how the syscall works. Whenever an application wants some privilege instruction to be executed, it requests for a system call. The kernel, it executes the syscall, and then it sends it back to the app. Okay, so this is how it works. So let's look at this in a more, in a different perspective. So it's nothing but it's kind of a function call itself, right? So it's kind of a function call except that the function has to be executed by the kernel. So we know what a function call is. So let's say there's some function called main, and this main was executing some instructions, and suddenly it comes across a function called f1. We know what to do. What happens is, whenever this instruction, whenever we have a function calling another function, we jump to a different set of instructions that need to be executed, which are nothing but the instructions corresponding to the function f1. Okay. So that's exactly the same thing that happens here, except that this main you can view as a user application, and this function is a kernel application or kernel function. So this piece of code that has to be executed will be executed in the kernel space. Okay? It's not in the user space, it's the kernel space. So that is the difference. So far this program was in the user space, but this is in the kernel space. Okay? Right. And what is this f1 function? It's some function that is known to the kernel. Okay. So there are a list of functions which the kernel knows. Okay. So let's say, so out of those functions, say f1, f2, f3, and so on up to some fk. So these are a list of functions which is available to the kernel, and the kernel knows about them. So what the user program has done is it has invoked one among these, and these functions that we are talking about are called system calls. Now, when this function is executed, or this function is the application request for this function, this is nothing but kind of a software generated interrupt. That is, the user application which was running so far gets it halts, and the control jumps to the kernel. The kernel then executes the function. But as we know that during interrupts, before you make a jump, even in case of normal function call, what happens is whenever you jump from one function to the other, there are something that need to be done before you start executing this function corresponding to f1. What is it? The state so far. Okay, and when I say state, I mean the contents which have been obtained so far and which are present in some locations have to be saved. So before you make a jump to the system call, so before the sys call is executed, there are something that needs to be done. What is it? And you have to save the state. Right? So that's the first thing that needs to be done. The states have to be saved. What do we mean by save? The contents of the different registers. So we have different register contents, the memory contents in some cases, maybe. Now this have to be saved. Okay. So that's the first thing you do. So that when you come back, you get these values, or else they will be overwritten by the new values which have been generated during execution of this code, okay? The code to which you have jumped. So that has to be done. Then you have to save the return address. Because you would like to come back to the execution of the main program again. So you should know where should you return to. As in this case of the normal function calls, once you get back to this, the next instruction that needs to be executed is this line. So you should know where you should return. And that's exactly what is done in case of system call as well. So remember that system call is also a software generated interrupt. During a system call invocation, the first thing that is done is the the state of the program so far, the user program is saved, then the function, that is the system call, that has to be invoked. We jump to that particular, before that the CPU switches its mode from the user mode to a kernel mode. The kernel code is executed, and before that obviously the return address has to be saved. So let's quickly summarize. Look at the system call implementation. Okay. So as we know that system call is the mechanism through which an application interacts with the kernel. So whenever an application needs to execute something, it puts a system call request, and the kernel, it executes the system call, okay, syscall, and then it sends it back to the. During this process, we know that the CPU switches its mode from a non-privileged to a privileged. But let's see how the system call actually gets implemented. Okay. So let's say there is some user program. Okay. So say this is a user program, and the user program has certain instructions, and one among them is a read instruction. So this is a system call. So the moment the system call is, say the system call is requested. Okay. So the moment the system call is requested, we know that there must be a mode switch. Right? So the process goes into the privileged mode or the kernel mode, and the kernel now has to execute this system call. So this is where things take a turn. Now, because this system call is a software generated interrupt, right? You already have seen that system calls are software generated interrupts. And as the case of any interrupt, you need to have some kind of an interrupt vector, which would tell that what is the corresponding interrupt service routine. I mean, what is the interrupt service routine corresponding to that particular interrupt. Okay, so exactly the same thing happens here. So now, the moment this read instruction is being read by the kernel, okay, so it's a trap, right? Or it's a software generated interrupt, say, which is interrupting the execution of the current instruction, and the CPU is told that now some other instruction has to be executed. But how does the CPU know which instruction? So here we have an interrupt vector. So that's the syscall entry, you can say, which is maintained by the OS. So the syscall entry, or you can say the interrupt vector. So mode switch and say the syscall entry is looked up. Put it in this way. Syscall entry is looked up. Okay, and once the OS can identify that, okay, this is the interrupt that has come, that is the corresponding system call, and it looks up that this is where its interrupt handler is, then it looks up into, so this is the system call table, so it actually takes up to this entry. This is the syscall table where the corresponding mapping is being maintained, and once the entry is identified, so it jumps to that corresponding code, and the code that corresponds to this read system call, and once it is being done, the code is finally sent back to the app. So what we have, so the fourth one is where we have return from the service function. Fifth is return from syscall. So let's summarize. The moment a system call is invoked, it's kind of a software generated interrupt that is sent to the OS. The CPU switches the mode. The OS looks up into the system call entry, that's the interrupt vector, and finds out the corresponding interrupt handler for that particular syscall. It looks up to this entry, jumps to that code, so the system call function, and once the function is executed, it returns and returns back to the application. So this is how a system call gets implemented. So there are a lot of system calls with which we will be working with. Some typical examples of system call are, you already have seen some of them. Write, okay, and we have read. So these are two file management related system calls. Later on, we'll in the next lecture itself, we'll be talking about some process related system calls, and we'll come across some system calls such as for, then execute and exit. Three related to process management. So these are the very simple system calls that we'll be talking about. And by the way, I did not mention how the system calls are executed. I mean, the system calls are, we now know that how system calls are executed, but okay, so let me complete this. Okay, so the system calls are mostly accessed, through high-level programming interface. So we have seen so far, I mean, in the programs that we have been discussing so far, you must have realized that though we have a system call called write, but we usually do not use these kind of system calls in our program. Rather, we take help of some kind of programming language support. So that is, we use some kind of high-level APIs, okay, are used to access the system calls. Say, for example, instead of using write, we use printf. So instead of write. Now, what is the reason for that? No, reason is that these application programming interfaces are much easier to use. Developers or programmers, they usually find working with these APIs more easy as compared to working with the system calls. So that is one of the reasons why. So the primary reason is ease of use, and the system calls are mainly error prone. Okay, they are very complicated, so it's better to avoid that. If we have some facility, a more simpler one, it's better to use this. And one need not remember the I/O operations. So that is the most interesting part. So in case of the system calls, you need to know a bit details about the input-output mechanism, which you can simply do away with while you use these library functions. Okay. This is a library function which doesn't need to have any information or any idea about the input-output. So that is the reason why people usually prefer use of APIs rather than system calls, or library functions rather than system calls. Okay, so that's about the fundamental concepts. From the next lecture onwards, we'll go a bit deeper into the understanding of processes, and we'll start off with a detailed discussion about process and different APIs which are available in different operating systems, which will help us in working with different processes. So that's so from next lecture onwards we'll be starting off with the topic on process management.